wonderful person, this is Anton, and today we're going to discuss a fundamental shift in what we understand about intelligence. And that's because for a very long time, we assumed that to be smart or to be intelligent, someone or something had to be able to solve different problems or had to be able to make decisions by using a brain, or at least by using some kind of a nervous system in order to produce these complex behaviors. But as scientists started to explore the natural world a little bit more, they started to discover examples where intelligence seems to manifest without a brain, without any center, or as a matter of fact, without any center or any control mechanism, with certain organisms being able to exhibit intelligence, even though in theory it should be impossible because there is nothing controlling anything. And so in this video, we're going to explore several examples and several recent studies about this, first focusing on this very recent study that essentially shows us that all of this can actually even be mechanical and seems to emerge from the laws of physics itself and not from some kind of a central controller. And so here let's actually start with this recent example that was just released in a study you can find right here. The study by Lisa Schick and a team from Germany and USA. And this essentially involved an organism we've discussed several times before, and the organism that just does not stop fascinating us. Something that actually starts as this. One of the most fascinating creatures on the planet, referred to as Physarum polycephalum, although much more commonly referred to as the yellow slime or slime mold. A really strange and difficult to understand organism that's technically just one big cell, but that exists in a kind of a form referred to as a plasmodium, or essentially a single cell that contains multiple nuclei inside and is able to then form very bizarre shapes such as this unusual branching web of yellow goo, but can also result in a variety of shapes. Or in other words, it's as if many different cells join together to create a single cell that then starts to reshape itself in many different ways. Although for pretty much most of these types of organisms, this is just one of the parts of the transformation cycle during their reproduction and growth. So as you can see in this image, following this plasmodium stage, they then become sporangium in order to create additional spores and to then spread somewhere else. But intriguingly, despite having no neurons inside, and literally just being one single cell, we know that this bizarre organism can actually do some really crazy stuff. For example, it's able to solve mazes and different types of puzzles, such as a famous experiment involving the map of Tokyo, where the slime mold was able to connect each individual area in Tokyo, creating something that resembled Tokyo subway. In other words, it was able to optimize for the shortest possible paths and recreate something that took humans a very long time to create in mere hours. Although to be more fair, in this case, each of these individual white spots that represented different parts of Tokyo were essentially different food chunks that the slime mold tried to eat. And it was really through this eating process that it then created this beautiful map. But on top of being able to solve problems, it also exhibits a type of memory, which is also a little bit surprising because once again, there are no neurons inside, and this is literally just a single cell. And so for a very long time, scientists were trying to understand exactly how all of this happens, and what's the main principle driving all of this, which is what this June 2026 paper is all about. Here, scientists wanted to take a glimpse at the actual mechanical principles behind these so-called decisions. And to do this, researchers created a very clever experiment. First, they remembered that this particular slime mold does not like blue light. And so they actually created a kind of a blue light trap. And so here they trapped this organism in different types of geometric shapes created by these blue light objectives. So things like squares, hexagons, and triangles. And here the slime mold, that was basically driven by hunger, was very desperate to escape. And so here scientists discovered that in almost every single case, the slime mold chose to escape along the longest axis of whatever shape it was trapped in. But apparently this was not some kind of a decision, or basically this was not some kind of a choice. It turns out that all of this is basically mechanical. As scientists later discovered, this was a result of a very simple mechanical process, because the slime mold uses something referred to as peristaltic contractions. You can sort of see what it's doing here. In other words, it's a kind of a rhythmic squeezing of their body in order to push internal fluid inside the cell. And while during the exploration phase, the slime mold actually tries pushing in almost every direction because it's trying to increase its chances to find food. But because now the environment kind of had a major constraint created by this blue light, the study discovered that as internal fluid was flowing inside, the organism then settled on a kind of a contraction mode that is usually most efficient for transport, and inside a confined geometric shape, this efficiency is usually along the longest axis. Here it basically builds up the most fluid pressure, which can then finally burst through the light barrier. And so, in other words, the slime mold was not really thinking and was not making decisions, but instead it was just a liquid inside exploring various physical states until the physics inside its own body found a path of least resistance and highest pressure, at which point it basically just bursts. And so, in some sense, it's an appearance of intelligence, but is all purely mechanical in nature. No brain and no central decision-making required. But this idea of unusual intelligence goes a little bit further with this other recent article that you can find in the description about ants, and specifically ant queens. And that's because these complex behaviors can also be observed in ants and a lot of other social insects. And so here let's also discuss the idea behind swarm intelligence that sometimes happens in a lot of different animals. And here this intelligence also emerges from these very simple rules, normally the result of some kind of a decentralized collective behavior. And in this case, there's this very common misconception in regards to queens, or basically that the queen ant or queen bee is some kind of a centralized leader or some kind of a literally queen that then tells other ants or other bees what to do. In other words, we think of a queen as a kind of a leader that guides everyone. But in reality, the queen is not in charge at all. As a matter of fact, usually she only has one single role: reproduction. Her only role is maintaining the workforce by producing new ants, or, in case of bees, by producing new bees. And well, sometimes when something happens and the queen becomes less productive or somehow becomes disabled, the workers can easily replace her and usually actually kill her in the process. In other words, when it comes to ants, they don't actually care for the queen's orders. And that's because ant colonies solve incredibly complex problems, like for example building climate control nests and optimizing transportation networks, without any actual central manager such as the queen. And here they use a process very often referred to as stigmergy, a form of decentralized communication where each individual responds to various cues left in the environment by others. And that's because when ants forage, they leave behind what's known as a pheromone, a tiny molecule that's usually perceptible to other ants, so a kind of a scent hormone. And so as other ants follow these trails, they usually add more pheromones, making these trails stronger. But because pheromones evaporate and get destroyed over time, a lot of short paths are usually reinforced quickly, but the longer ones take longer. And this actually creates a lot of different, very simple feedback loops, allowing the entire colony to then discover some of the most efficient routes to find food, or some of the most efficient ways to create some kind of a structure. This usually applies to other social insects, such as, for example, termites. And this is actually without any single ant visiting the entire area, but instead it's the collective that then creates these very efficient structures. And even for animals like termites, individual insects do not actually have blueprints or understand architecture, but a lot of these local rules of building something and communication via pheromones allows them to construct some of the biggest biological engineering marvels on the planet. And so based on some of these recent discoveries by entomologist Tanya Letty, we now are pretty certain that despite the title, the ant queen, the termite queen, or the queen bee is not a boss or a manager, and is only there to lay eggs. And instead, this is a process referred to as decentralized self-organization, where individual ants, termites or bees follow simple, localized rules based on various chemical signals. But the reason we're seeing this complexity of behavior and something that even appears intelligent is basically a kind of an emergent intelligence that exists in a lot of different superorganisms. But in this case, what's actually intriguing is a comparison between a typical ant swarm and a human swarm. Or basically what's actually remarkable is how these decentralized systems tend to scale. And there was even a study that tried to recreate this using humans and ants. And here we even have a video demonstrating this. And basically the point was to solve the maze, with the main task being moving objects through very tight spaces, and doing so as efficiently as possible. And surprisingly, for humans, performance seemed to decline as the group got bigger. This is a phenomenon referred to as Ringelmann effect. But for ants, the effect was the opposite. As ants increased in numbers, they actually got better and better at solving this puzzle and did so much faster and more efficiently. And that's because in a swarm, there is no single point of failure, and so if one ant fails, the colony still continues. This is the main principle behind this distributed cognition, with this idea of intelligence and decision-making now being offloaded into the environment and shared across the entire group. And so the intelligence here becomes a property of the entire system, not each individual ant. And this actually redefines our initial definition of intelligence that's often been described by a factor known as G, or general intelligence, which only apply to individuals like, for example, a single human or maybe a single dolphin or an elephant. But a lot of these new discoveries now suggest we actually need to look at intelligence as a kind of a optimization power, or basically the ability to achieve goals in a lot of different environments, independent of whether you have a brain. So basically we now have a kind of a C factor, or collective intelligence. And this is of course something biologists have observed in many different systems out there, from for example the so-called wood wide web, which is basically a fungal network that usually exists underneath various forests and connects each individual tree with this massive network of mushrooms, with actually older trees very often providing for the younger trees and giving the forest a kind of an ecosystem and a kind of a distribution network, or even bacteria that tend to detect and react to various chemical signals using molecules known as autoinducers. And normally, by counting how many of these molecules are in the environment, bacteria tends to experience something referred to as quorum sensing, or basically they actually start to act in unison and create complex and relatively large structures, or even coordinating behavior, such as suddenly becoming pathogenic and attacking something else. Which naturally has quite a lot of implications for what we think intelligence is, and I guess in much more broad strokes, what we now understand about the idea behind artificial intelligence. As in this case, we don't really have to build some kind of one massive centralized superbrain, and instead might want to focus on some kind of artificial swarm, and using a bunch of simple algorithms that potentially are modeled after ants or even slime mold in order to solve various problems and in order to provide various complex solutions. And so by studying these brainless organisms such as slime mold, we're actually learning how to build these decentralized autonomous systems, and are also getting just a little bit closer to being able to define the idea of intelligence that seems to apply to everything on the planet. And so in the end, it really seems that intelligence is not just some kind of a thing you have in your head, but seems to be a much broader phenomenon and involves a complex process of interactions involving the organism and its environment. Or basically some kind of an interaction between individuals, cells, or even molecules, which basically suggests that, in theory, the entire universe is actually full of these decentralized systems, or these decentralized architects, that could manifest in a lot of different ways that we cannot imagine. And so in some sense, that of course could be good news for trying to find intelligence somewhere out there. Or basically extraterrestrial intelligence could actually exist if we find a better definition for intelligence. Maybe aliens don't need a brain because that alien intelligence can still manifest itself in the same way as it does in this slime mold, through some kind of a mechanical or chemical process that involves an elegant application of physics and simple local rules. But apart from these studies, everything else at this point is just a speculation. But we'll still come back and discuss this more in some of the future videos once there are some additional studies. On that note, thank you for watching, subscribe, come back tomorrow to learn something else. Support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support this channel by buying the Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.